Hello, my name is Taylor Harvey, and I'm a PhD student at the University of Florida in Dr. Andres Inkvist's group. This is my poster on the development of a prototype simplified neutron scatter camera for nuclear safeguards applications. So a bit about the introduction and motivation of this project. So a neutron scatter camera is a type of neutron imaging system that can provide valuable spatial information about neutron sources for safeguard scenarios. So that's scenarios like verification of warheads or search scenarios and lost source situations. Many systems with this concept have been developed, but most are large, expensive, or have a complicated readout, making the widespread adoption of this type of system kind of impossible in many cases. So this project seeks to build a simplified, less expensive prototype neutron scatter camera that can perform satisfactory source localization. So a bit on the principle of these physically work. So essentially how a neutron scatter camera works is a system detects two consecutive neutron scatters from a single neutron emitted from a source. So in this example here, we have a Californium 252 source, which is a spontaneous fission source releasing fast neutrons. The neutron in this case comes along this black vector here until it scatters in the detector and then scatters a second time. Now, based on the kinematics of these two scatters, we can back project what are called probability cones or back projected cones to get an idea of the source direction. And the way we find these scatter locations is by comparing the light arrival timing and the pulse heights of PMTs or any kind of photodetector that are mounted to the different sides of the detector. So we can find the scatter locations and the scatter energy deposited in 3D space. The relevance of this mission is to make an affordable mobile neutron imaging system that can be used in managing nuclear materials, treaty verification, accident response, external reactor core monitoring, or security in smuggling or diversion scenarios. So a bit about the actual development of this prototype. So originally, simulation was done using MCMP Polimi to find if this type of design is possible. And going forward from that, we developed a cube-shaped fast plastic stimulator based on EJ230, which is a fast plastic chosen for its good timing and relatively high light yield characteristics compared to other fast plastics. So as you can see in this image here, this is just a picture of the detector system as it is now. As you can see, there are 6 PMTs coupled to each of the 6 faces of the detector. The 6th PMT that you can't see in this image is in this box below. And basically, you find out these scatter positions by comparing the light arrival times and the pulse heights of scatters produced by 2 consecutive neutron scatters. Now, the reason we need a fast plastic is because in general, most scintillating materials and digitizer systems don't allow for a proper time resolution to resolve scatters that are just a few nanoseconds apart. But this fast plastic actually does allow us to see these secondary scatters. Although they're rare, we can use an algorithm to find likely candidates for double scatters, and using that data back project these cones that we need to create images. So this prototype has been quite successful in its imaging ability. We can look down here at a few images produced. So what you're seeing here is essentially a projection of the space surrounding the detector. And the azimuthal angle represents the area around these 4 PMTs here. And of course, the polar is measured from the top to the bottom PMT. So what you're seeing here is basically a source is placed at this red position here. And as you see, by back projecting these cones and creating this image, we can get a reasonable idea of the direction of the source. Similarly, in this image on the right, this is the same idea, but with a different source location. And this is done with several factors in the algorithm quite different. This one actually allows you to see some of the impressions of the annuli that go into generating this image, while the left kind of uses more cones and it kind of subsumes the individual detail from the annuli. The point of this is to show that using 60 cones, which is quite a lot actually given the efficiency of the detector, you can get a pretty reasonable knowledge of the location of the source. While using about a fourth of as many cones, you can get also an idea of the general direction of the source, but not quite as well resolved. As you see, there's kind of several different potential hotspots for this source at this location. As I mentioned, different settings for the detector, that's kind of illustrated here. This is basically an efficiency curve of the number of particles detected by the system, a number of useful cones produced divided by the number of particles detected by the system. That's what I'm calling useful cone efficiency. And so this is basically an efficiency curve that shows, as you'd expect, as you raise an energy cutoff, you see less total cones. But when you have a higher energy cutoff in these regions down here, you have more confidence in each individual cone is going the correct direction. Most of the images that we've been successful in localizing sources, like the ones you saw down there, are run in this region here. So that's a relatively high ratio to first peak to second peak, meaning that the second peak has to be quite high compared to the first peak, and also a low first peak cutoff. So really allowing any first scatters that we see to go through and generate these cones. So a little bit on the actual data we found so far. The prototype seems to be capable of localizing neutron sources using a plastic simulator volume and just standard PMTs. The best achievable resolutions we've been able to generate from images we've seen so far has been a 27.1 azimuthal angular resolution and a 16.5 polar resolution. That's pretty adequate for finding a general direction of a source. It's nowhere near detailed enough to kind of tell you the shape and the exact identity of the source just based on the image, but it is would be valuable in certain scenarios. The timing resolution, which is relevant for finding the many of the features of the back-restricted cones, was found to be 0.8 nanoseconds. And we found the best results in these images with a two-step imaging procedure. So first, we make a guess of the source direction based using all of the pulses. So basically, we look at the pulse height of the PMTs relative to each other, using every single pulse we see, whether it's a double scatter or not. That gives us an initial guess vector that's usually gives us a general direction that the source is likely in a single source scenario, that is. And then our second step is to use that vector to bias our images and thus throw out noisy cones that we generate that are going in the completely wrong direction. And that improves the image quality quite a bit. And that was used to generate these images you see here. As far as the next step for this project go, we want to further quantify the camera's angular resolution for distributed and multiple source scenarios. So all of these measurements so far have been just using single approximate point sources of californium. And we want to see how the images look different for more distributed sources and sources where there's multiple sources around in different directions from the detector. We also want to quantify the measurement times necessary to produce useful images at different source strengths and standoff distances. That we kind of have done a little bit as far as the efficiency curves up here go, but what we really want to do is find out how much time you need to generate these images. So these images were several hours long, but we think that it would be possible to get a very rough image in a lot shorter amount of time as that. We also want to explore some alternative photo multipliers. So instead of just using these standard PMTs, perhaps look into changing this out with SIPM or other newer photo multipliers. So that concludes my presentation here on this poster. Feel free to reach out to me with any questions. Thank you.